From prehistoric times to the present, optical communications have greatly influenced human culture. For centuries, ancient peoples communicated through fire and smoke signals. In the 1850s, Alexander Graham Bell invented a device for sending voices over beams of sunlight. Today, a century and a half after Bell's photophone, we are beginning to exploit the full potential of optical communications using fiber optics. Today, you can find optical fiber everywhere, from long-haul telephone systems to small inter-office networks. A global fiber optic infrastructure is now reaching out to individual homes and desktops with the promise of exciting new services never before possible. Fiber optics are also finding a multitude of applications in industry and medicine, from machine vision and measurement to the delivery of high-power laser beams in cutting systems. To understand fiber optics, we must first review some important characteristics of light. The visible light we are all familiar with makes up only part of the electromagnetic spectrum that encompasses energy from radio waves all the way up to X-rays and beyond. All electromagnetic waves move at the speed of light, which is about 186,000 miles per second. The difference lies in the distance between the crests of individual waves, known as wavelength. In the visible part of the spectrum, the wavelength of light determines its color. Optical wavelengths are measured in nanometers, or billionths of a meter. Blue light has wavelengths of around 400 nanometers, while red light is approximately 700 nanometers. The infrared area starts around 800 and increases to about 100,000 nanometers as it approaches the microwave region. It is the infrared area we are interested in for most fiber optic applications. When light passes through various materials, its velocity changes. Light traveling through a vacuum moves faster than light traveling through denser materials such as glass. The abrupt slowing of the light at the vacuum glass interface causes it to bend slightly. This effect is known as refraction. The degree of bending is dependent on the ratio of the light velocities in vacuum and glass. The ratio, called the refractive index, is symbolized by the letter N. Glass can be doped to create materials with refractive indices tailored for specific applications. In this example, we see the refractive index calculations for two common types of glass used in optical fiber. Various wavelengths of light will respond differently to the refractive index of a material. When white light, made up of many wavelengths, passes through a prism, the refractive index bends shorter wavelengths like blue and violet more than green and red, resulting in the familiar rainbow display of colors. When a beam of light strikes a refractive material, the direction of the refracted light will depend on the angle of incidence of the light beam. As this angle changes, so does the direction of the refracted light. At a certain critical angle, the light no longer passes through the interface between the two media, but is reflected as if the interface was a mirror. The critical angle will be different for various materials and is dependent on refractive index. The critical angle is responsible for the interesting optical phenomenon that makes fiber optics possible. In 1854, John Tyndall discovered total internal reflection. His experiment consisted of a container of water with a hole near the bottom and a source of light. Light entering the water stream at the critical angle between the air-water interface is totally internally reflected, allowing the water to act as an optical waveguide. Modern fiber optics exploit this natural process. An optical fiber is made up of three parts. The first is the buffer coating. Made from plastic materials, the coating provides protection against bending and mechanical stress. Under the buffer coating is a layer of cladding, usually made of pure silica glass. The innermost part, the core, is also made of silica, but is doped with certain elements to provide a refractive index usually higher than the cladding. The difference in refractive indices between cladding and core forces light to be totally internally reflected along the fiber waveguide. Light launched into the fiber within a small angle of its axis will be transmitted to the opposite end. The sign of this angle is called the numerical aperture, which defines a cone of acceptance at the fiber's end. Light that enters the fiber from outside the cone of acceptance will not be transmitted, but instead will be refracted out through the cladding and be lost. The structure and chemical makeup of the core is critical to fiber operation. Optical fibers are divided into two broad categories, multimode and single mode. The major difference between them is the diameter of the core. Single mode fiber has a small core diameter compared to the overall fiber diameter. The small core size forces light to travel in a single pathway or mode down the axis of the fiber. Multimode fiber has a much larger core diameter, allowing light to take a number of pathways from one end of the fiber to the other. The fundamental mode travels down the fiber axis, while higher order modes can take a number of alternate pathways. When a short pulse of light is launched into a multimode fiber, the axial mode arrives at the other end first, followed by the higher order modes. This has the effect of stretching the optical pulse, known as modal dispersion. Modal dispersion limits the usefulness of the fiber at high transmission rates when pulses begin to overlap and garble the information carried. The effect increases with fiber distance. For this reason, single-mode fiber is the preferred choice for long-distance, high bitrate transmissions, as it is not affected by modal dispersion. Another type of pulse spreading is chromatic dispersion. This occurs because different wavelengths have different propagation times through a fiber. Pulse spreading due to chromatic dispersion of infrared wavelengths is very small, so it only interferes with transmissions of extremely high bit rates much too fast for multimode fiber. In single-mode fiber, however, chromatic dispersion can be a major problem. Conventional single-mode fiber has been optimized for minimum dispersion at 1300 nanometers. Dispersion-shifted fiber and non-zero dispersion fiber are optimized for use at 1550 nanometers. To further reduce the effects of dispersion over long distances requires the use of laser light sources. Lasers produce light of a single wavelength, or a very small range of wavelengths, compared to an LED source. Referred to as line width, the range of wavelengths produced by a light source is a measure of its spectral purity and suitability for single-mode fiber systems. Single-mode fibers will propagate a single mode only when the wavelength of the light source is longer than a certain value. As wavelength gets shorter, the core has more room for higher order modes to propagate. The cutoff wavelength is the minimum wavelength at which the fiber will support only one mode. The use of sources shorter than the cutoff wavelength turns a single-mode fiber into a multimode fiber where modal dispersion again becomes a problem. Thus, it is important to match single-mode fiber with the proper wavelength sources. To reduce the effects of modal dispersion in multimode fibers, manufacturers can alter the chemical makeup of the fiber core. In the original step index type of fiber, the refractive indices of core and cladding change abruptly at their interface. This type of construction costs less to manufacture, but has the highest dispersion. It is used primarily for short-distance, low-speed applications such as industrial controls. In a graded index fiber, layers of glass with smoothly varying refractive indices comprises the core. Because the core center has the highest refractive index, the axial mode is slowed down, while higher order modes travel faster, so all modes will arrive at the end of the fiber closer together. This reduces modal dispersion, allowing long-distance fiber runs or higher transmission speeds. Because single-mode fiber does not need to address the propagation times of high-order modes, it also has a step index construction. However, unlike multimode fibers where optical power distribution is entirely within the core, light transmission within single-mode fibers assumes a Gaussian distribution. Approximately 80% of the light travels within the core, while 20% travels in the surrounding cladding. The diameter of the light spot carried is called the mode field diameter. Fiber manufacturers' specification sheets may detail both single-mode core and mode field diameters. The larger the mode field diameter, the easier it becomes to splice and connectorize, but the more sensitive the fiber is to bending losses. Optical fibers are available with a number of core and cladding sizes, designed for various applications. Single-mode fibers are made with core sizes ranging from 8 to 10 microns and a cladding size of 125 microns. Because a wide range of multi-mode fibers are available, the fiber is specified in micrometers with core diameter first, followed by the cladding diameter. Common multi-mode fibers include the 50-125 and 62.5-125 types. The 50-125 fiber is generally considered as the European standard for communications use, while the 62.5-125 type is the North American standard. Other types used for low-speed applications include the 100-140 and the 200-230, both used in industrial controls and low-speed data networks. Fibers with large core sizes can handle larger light volumes, higher optical power levels, and are convenient for use in fiber optic signs and the delivery of laser beams for surgical or industrial applications. Fibers can also be made from plastic materials, offering low cost and ease of use. Today, 1,000 micron plastic fiber with a 980 micron core is well entrenched in lighting, signage, and automotive applications. It is now becoming a serious competitor to Category 5 UTP wiring, providing an optical alternative for short-distance networks. There are a number of methods used to make glass optical fiber, based on the chemical vapor deposition process, or CVD. With the inside method, ultra-pure silica, germanium, or other elements are vaporized and applied to the inside of a silica tube heated by a hydrogen flame. Each pass of the heat source fuses a small amount of raw materials to the inside of the tube as a thin layer of glass. The composition of the vapor is designed to create layers of glass with a refractive index usually higher than the silica tube. These layers will form the fiber's core, while the tube becomes the cladding. When enough core material has been built up, the tube is strongly heated to collapse it into a solid rod called a preform, which is a scale model of the finished fiber, only much shorter and thicker. The preform is then installed in a drawing tower, where it is melted and stretched into an optical fiber many kilometers in length. In the outside deposition process, vaporized raw materials are applied to a rotating mandrel, first to form the core, then the cladding in what is called a soot preform. The mandrel is withdrawn and the soot preform placed in a consolidation furnace, which collapses the center hole and fuses the particles into a solid, transparent glass rod. This preform can then be drawn into a continuous fiber strand. A recent development in fiber manufacture is the vapor phase axial deposition process, or VAD. A silica glass starting rod is rotated with its end initially in one or more hydrogen flames. Vaporized components flow through the torches and are deposited as sooty particles on the end of the rotating rod. As the rod moves upward, core and cladding layers are applied simultaneously to grow a porous soot preform with no center hole. The soot preform can then be consolidated and drawn into fiber. All optical fiber must pass rigid quality control tests before it can be used. Fiber that has high losses or is mechanically weak is rejected. The fiber can then be incorporated into cable structures. All transmission lines, including optical fiber, exhibit some loss or attenuation of a transmitted signal. In fiber, much of the loss is intrinsic, that is, due to the glass itself. However, external conditions, such as excessive bending, connectors, and splices, also contribute to signal losses. The dB, or decibel, is a measure of signal attenuation between the input and output. Fiber attenuation is expressed as dB per kilometer. Among the intrinsic losses present in optical fiber are absorption and scattering. Absorption is caused by impurities, such as metal ions and hydroxyl ions, introduced in the manufacturing process. The impurities absorb portions of light energy and re-emit it as minute quantities of heat. Absorption losses in fiber are highly wavelength dependent. Shorter wavelengths tend to be absorbed more easily by impurities in the glass. The use of infrared wavelengths dramatically minimizes this effect. This is why a majority of fiber optics used in signal transmission have been designed for infrared wavelengths. The most common wavelengths used are 850, 1300, and 1550 nanometers. These wavelengths were chosen for the best performance with light sources, optical fiber, and optical detectors. Scattering losses occur when light is reflected in all directions, including back toward the light source. Scattering can be caused by impurities in the glass or by reflective surfaces, such as fiber ends, breaks, or splices. The portion reflected back to the source allows optical time domain reflectometers, or OTDRs, to measure attenuation levels and distance to fiber splices or breaks. Other sources of attenuation in optical fiber are macro-bending and micro-bending losses. Macro-bending loss shows up when fiber bend radius decreases. As the bend gets tighter, light rays within the fiber begin reflecting at angles, allowing them to pass out through the cladding. The more the fiber is bent, the higher the attenuation. Microbending losses arise from stresses on the fiber, such as tight clamps, tie wraps, or rocks pressing against fiber cables. They can also be caused by deviations in the core, as measured from the axis of the fiber. Over the years, improvements in manufacturing processes have resulted in fiber with very tight tolerances in core and cladding geometry. Consistent fiber size is critical when using fixed V-groove alignment splicing or when assembling ferrule-type connectors. These devices rely on the outer cladding diameter to align fibers for connection. A difference of only a few microns in cladding diameters can result in a splice with unacceptable losses due to severe core misalignment. Differing core sizes also result in unacceptable attenuation at splices. When installing connectors, a cladding diameter of plus or minus 2 microns may require up to 5 ferrule sizes to be kept on hand. Otherwise, excessive space between fiber and ferrule would again result in unacceptable losses. Fiber cladding diameters are established during the drawing process. Today, manufacturers produce single-mode fibers with plus or minus 1 micron accuracy. Concentricity refers to how well the fiber core is centered in the cladding. Here, too, loose tolerances will yield poor quality splices and connections. Concentricity values are established during the deposition process and are usually less than 0.8 microns. Fiber curl describes the amount of curvature that exists along a given length of fiber. While all fibers exhibit some curl, excessive amounts can cause end-face offset in V-groove alignment fixtures. Concern with fiber curl was not an issue until the advent of mass splicing techniques used with ribbon fiber. Ribbon fiber consists of a number of parallel fibers sandwiched between adhesive tapes. Although a great time saver for high-volume production, mass splicing sacrifices individual control over fibers, requiring very tight fiber tolerances to get acceptable results. But why use fiber? What makes it better than other types of transmission line? Fiber has a number of distinct advantages over other methods of signal transmission, the most important of which is bandwidth. Bandwidth is a measure of the information carrying capacity of a transmission system. The amount of information that can be handled is limited by the frequency of the carrier signal. The higher the frequency, the more information can be carried. This is why microwaves can carry more signals than radio frequencies. Light has a frequency in the order of 300 trillion hertz. as compared with microwave's few billion and the 500 million offered by RF. Thus, many more channels could be modulated on a beam of light than on the highest frequency microwaves. The continuing development of optical fiber has resulted in fiber cable with extremely low transmission losses compared with the best copper conductors. Such low losses make it possible to construct transmission systems with tens or even hundreds of kilometers between repeater sites, as opposed to 700 meters for coax cable TV trunks. In addition, losses in copper cables increase with frequency, so the more information you try to force through a copper conductor, the higher the losses. Noise immunity is also poor in copper transmission lines. They are sensitive to the electric and magnetic fields generated by machinery, radio equipment, lighting, and high-voltage power lines. Ground loops and crosstalk are also severe problems in copper cables. Because glass is an insulator, no electric current can flow through an optical fiber. And because the optical signal cannot pass between fibers, fiber cables are immune to both optical and electrical interference. Fiber does not radiate signals, so it is extremely difficult for an intruder to tap into a fiber system. Light must be removed from the fiber itself, making detection very easy. Fiber affords a degree of security not possible with other transmission systems. One of the finer attributes of fiber is its size. Optical fibers are not much thicker than a human hair. Even when fibers are coated and incorporated in cable structures, they are far smaller and lighter than metallic cable. A copper cable with 900 pairs, carrying 21,000 telephone channels, has a diameter of 3 inches and weighs 8 tons per kilometer. An armored fiber cable with 12 pairs of fibers carrying over 290,000 channels is slightly over ½ inch in diameter and weighs less than 450 pounds per kilometer. Small size and light weight make storage, handling, and installation much easier. In most urban areas today, copper cabling has filled existing ductwork to capacity. By using smaller fiber cables, efficient use of inner duct space is ensured. Explosive environments present in chemical plants and oil refineries are perfect for fiber transmission systems. Because fiber does not carry electric current or radiate energy, it is the safest and most efficient method for providing connectivity in these applications. Fibers can be manufactured to reliably operate in temperatures from -40 to 200 degrees Fahrenheit. Temperature resistance from -100 to 1000 degrees has also been demonstrated. The performance of optical fiber remains stable throughout variable moisture conditions that would cause severe corrosion in metallic transmission lines. This eliminates the need for scheduled replacement of the cable. When John Tyndall first observed the curious behavior of light in a stream of water, he never could have imagined the impact it would have on humanity. Fiber optics have since permeated every aspect of our lives on this planet. In a constantly changing world of technology, new standards are evolving at a breathtaking rate. From digital telephone systems to high-definition television and imaging, from high-speed workstations to thousands of medical and industrial applications, fiber optics is the backbone of the global information infrastructure, the key to a future of unlimited possibilities.